Hi everyone, I'm Siddharth, and today I'm going to be talking about my work, which is variational quantum algorithms in the era of early fault tolerance. And this work was done in collaboration with my colleagues at Chicago, Georgia Tech, and Michigan. All right, so let's first start off with this notion of early fault tolerance. So by early fault tolerance, we mean a quantum device which can do more than just NISQ computing. But it's not quite all the way there, like in the fault tolerant era. So there is some element of error correction in there, but it's not all the way there. So the exact definitions for this notion vary, but for our purposes, for the purposes of this paper, we say that a device is in the EFT era if it has around 10,000 physical qubits and a 0.1% physical error rate. And these numbers have been taken from various quantum computing roadmaps for the next 3 to 5 years and are fairly representative. So now to understand how error correction is different in the EFT regime versus when it is done conventionally, let's take a look at both of them, right? So we can consider this to be a general quantum circuit composed of layers of Clifford and non-Clifford operations. And in the case of most variational algorithms, the non-Clifford gate is considered to be the RZ gate. So we're going to go ahead with that. So in the conventional error correction strategy, we implement Clifford gates using error correction, while for non-Clifford gates, we perform them via magnetic state distillation. Right. So the error correction step is relatively straightforward. You take the code patch as shown over here, apply some physical operation to a subset of qubits, and then end up performing the syndrome measurement and decoding and correction cycle over and over as shown. However, this strategy does not work for the non-Clifford case. We have to make use of a special resource state called a magic state. And the idea is to store this gate information, non-Clifford gate information M, in a logical state M, and then consume that state, so to speak, using this circuit as shown over here. But it turns out that if M is a general non-Clifford gate, these magic states are kind of hard to prepare. We cannot prepare arbitrarily high quality magic states. But if this M is a T state, then there are very well established protocols to prepare good quality magic state. So the next step is obviously to convert this RZ operation into a combination of Cliffords and T's, which is done via something like FritSynth. Now this leads to a really substantial increase in both circuit depth and gate count. Once we have this Clifford plus T decomposition, these high quality T states are prepared via magic state distillation, and the circuits that we use are called magic state factories. There is some problem with these magic state factories though, which is primarily the overhead associated with them, both spatial and temporal overheads. So for example, the best quality magic state factory here needs a physical qubit budget, which is 7 times the budget that we have available for us. There are other smaller magic state factories. For example, the one over here just occupies 8% of our budget. But then again, the quality of the factories is really poor. Like the error rate is actually worse than even 10 raised to minus 5. And of course, there are constant temporal overheads that we have to pay, ranging from 22 all the way to 228 clock cycles per T gate. These temporal overheads result in stalls, which effectively result in memory errors and degrade our program fidelity. So how do we get rid of all of these overheads? Well, a very straightforward solution is to not perform distillation at all. What do we do in that case? Well, in that case, the Clifford operations are performed as is using error correction. But for non-Clifford operations, we just inject a magic state. How exactly is this done? Well, the core idea is to take a surface code patch in an easy to prepare state, for example, 0 or the plus state, and straight up inject this arbitrary state RZ in it. There are like various ways to do this. We ended up using the strategy mentioned in Dinglingau and Ben Krieger's paper over here, but there are various other ways to do it. Now, the upside of this magic state injection strategy is that we don't have to deal with these long Clifford plus T decompositions. We also don't have to deal with distillation overheads because we're not performing distillation at all. But there's also a downside, which is that the error rate of this injection operation is comparable to the physical error rate of our system. And this is much, much worse than the error rates that can be achieved via magic state distillation. So in this context, we essentially have one central trade-off, which is at an application level. And this is like kind of what a VQE application would look like. At an application level is the fidelity loss from magic state distillation plus Clifford plus T decomposition overheads, worse than the fidelity loss from the highly error-prone magic state injection step. So in the Clifford plus T case, which is the conventional QEC case, as we call it over here, we have a lot of these small errors which might accumulate together to produce one large error. In the partial quantum error correction case, we essentially just have one highly error-prone operation. So let us see what happens when we evaluate this trade-off. So we perform this evaluation for variation circuits ranging from 12 to 24 qubits for 4 different magic state factories. And these are the factories which fit within our 10,000 qubit budget. These factories have been arranged in order of high quality, and the factories which have higher quality also have higher overhead associated with them. So the first thing we observe in this plot is, irrespective of the number of qubits or the factory, partial quantum error correction seems to be the better strategy. This relative improvement, which is the ratio of fidelity of partial quantum error correction to conventional error correction, is always greater than or equal to 1. However, the reason behind this ratio being greater than or equal to 1 depends on what factory we are looking at. So, for example, for the blue factory over here, 15 to 1733, this factory has pretty low space and time overheads. So just 900 qubits. So for a 24 qubit program, we can fit actually around 5 of these factories within our 10,000 qubit budget, which effectively reduces this 23 cycle overhead to roughly 4 to 5 cycles per T-gate. So program stalls are not really the big culprit over here. The problem is, though, that because there are such low overheads, we also have really poor quality T-state. So from a physical error rate of 10 raised to minus 3, we go down to a logical error rate of 5 times 10 raised to 4, 10 raised to minus 4, which is not even a one single order of magnitude reduction. This coupled with the fact that we have a really drastic increase in the number of T-gates. So like every RZ at this precision is around 50 T-gates long. So the net error from all these 50 T-gates really blows up your total error, and it ends up being worse than the error introduced in the partial quantum error correction strategy. Onto the red factory now. Again, for the red factory, the error rate is not the problem. We achieve almost a 5 orders of magnitude reduction in error rate via this factory. But the problem is that it has a substantially high overhead, around 4,400 qubits and 43 cycles per T-gate. So we can effectively just fit one factory within our 10,000 qubit limitation. Now, at this precision, the 10 raised to minus 8 precision, each of our RZs would have around 90 T-gate, which results in around 4,000 stalls per RZ operation. Of course, in an application level, the number of these stalls would just be multiplied with the number of RZs you have. And this is a lot of stalls, a lot of memory errors, and that really degrades your overall program fidelity. So the degradation in program fidelity is not as bad as in the blue case, but it is still, the fidelity is effectively still worse than the partial quantum error correction case. There's also a bit of a sweet spot here, which is, for example, this green factory, where both error rates and overheads are kind of manageable. But even for this green factory, we see that the relative improvement increases with the number of qubits. All right. So this is the first trend that we observe from our data. The second trend we see is that irrespective of which factory we look at, this relative improvement increases with the number of qubits that we have in our system. Why is that? Well, we'll illustrate this using the example of, for example, a 12 qubit circuit and a 24 qubit circuit. Variational algorithms, the number of RZ increases with the number of qubits in the program. So for example, the number of RZs in the 24-qubit program are twice the number of RZs in the 12-qubit program. The fidelity is proportional to this expression as shown over here, and the relative improvement is proportional to the ratios of this expression for the partial quantum error correction and the conventional QEC case. We saw in the last few slides that this ratio is always greater than 1 for a variety of reasons, be it the quality of T states or the amount of stalls in the circuit. So this thing would just increase as the number of RZ gates are increased. There's also a more subtle thing which influences the increase in relative improvement, which is that when the number of program qubits are small, we have a larger amount of space to fit in distillation units, which results in smaller stalls in our program execution. We don't really have as many memory errors. But as the number of program qubits are increased, we'll be able to fit lesser and lesser number of magic state factories, which increases in higher stalls and potentially high memory errors and less fidelity in our program. All right. So now we see that for our definition of EFT or early fault tolerance, partial quantum error correction seems to be the better strategy. However, we know that at scale, conventional QEC has the potential to offer exponential suppression in errors, and there will be a crossover point when it ends up being better than partial quantum error correction. So where is this crossover point achieved and how we achieve that? Well, for conventional QEC to perform better than partial quantum error correction, we need two things. We need high quality T state factories so that we have high quality T state, and we need a lot of these factories so that we don't really encounter memory errors. The way that these two things can be done is by making our T state factories either smaller or just increase the number of physical qubits that you have available. Both of these things result in us being able to fit more factories in the available space, which leads to a higher throughput, which leads to less stalls and hence less memory errors. Also, we are assuming that the T state factories are high quality already, so we are assuming that the T state error is low already. Well, let's look at one of these alternatives, which is magic state cultivation. I recently proposed idea by Guinea et al., which essentially reduces the size of these magic state factories. The spatial overhead is low, the temporal overhead is still pretty high because there are multiple rounds of post-selection that are needed, very high discard rate, which results in a large temporal overhead. Anyways, we can fit a lot of these factories in our given available space, which again means higher throughput, less stalls, less memory errors. What it leads to is that now there is a crossover point. So earlier we saw that conventional QEC was worse all the time. Now we see that for programs of size less than or equal to 20 qubits, conventional QEC is the better strategy. As the number of program qubits grows and the space to fit factories reduces, we see that partial quantum error correction ends up being the better strategy again. Well, what if we also increase the number of physical qubits available in our system? So now we go from 10,000 to 20,000 physical qubits. This means that we can fit even more cultivation units in there. The end result is that this crossover point shifts further to the right to around 37 qubits now. And if we keep extrapolating this trend, continuously keep increasing the number of physical qubits in our system, this crossover point will shift further and further to the right, and we'll see that the conventional quantum error correction strategy is better, as it should be at scale. All right, so this was comparison against conventional error correction. We also show results for comparison between partial quantum error correction and NISQ style execution. We showed these results for the Ising model Hamiltonian, where our metric for comparison is what we call relative improvement, which essentially quantifies how close a strategy, either be it NISQ or partial quantum error correction, how close it is to the reference energy. So higher is better. For the Ising model Hamiltonian, up to 100 qubits, we see that we consistently perform better than NISQ style execution. Similar results can also be seen for the Heisenberg model Hamiltonian. We also propose some VQA-specific architectural optimizations in our paper, which I won't be able to cover because of lack of time, but we also propose an efficient layout. patch shuffling, and locality and layout aware ansatz, and all these optimizations help us in reducing the qubit cycle overhead of executing VQAs in the early fault tolerant era. So to conclude, we adapt the ideas of partial quantum error correction for the purposes of variational quantum algorithms. We show that partial quantum error correction works better than both conventional error correction and NIST-style implementation in the early fault-tolerant era. We also introduce some architectural optimizations like efficient layout, patch shuffling, and a layout-aware ansatz. And we show that these optimizations reduce the qubit cycle overhead while preserving fidelity. Thank you.